Equipped with the corollary from Gauss' lemma, we can now prove that geodesics are locally length minimizing. But remember, previously we said that that will follow from the fact that radial geodesics are minimizing. So now we just need to show that radial geodesics are length minimizing. And remember, what does that mean? That means that, let's say I have a geodesic ball centered at P. That ball, I can take a point Q and then look at this geodesics starting from P, right, going to Q. Now, let's say I have another curve from P to Q. Let's call it sigma. Then the claim is that the length of sigma has to be greater than or equal to the length of this gamma V. If we let this gamma V has unit speed, right, and then let's say gamma V at time r is equal to Q, then that would mean this length is just equal to R. So what we're saying is that we need to show that for any admissible curve sigma from P to Q, the length of sigma has to be greater than or equal to R. So let's do this. Okay, so let us be kind of hand-wavy and just talk about the general idea of this proof. Fill in the technical details later, okay? So now we want to show that this length is greater than or equal to this length, right? Greater than or equal to R. It suffices then to show that this piece of sigma has length greater than or equal to R. We can figure out that arc length by integrating this velocity vector, right, on some interval. Now, by Gauss' lemma, we have an orthogonal decomposition of this velocity vector in the two directions. So one is in the direction of tangent to this radial sphere. Right, so one is this direction, and the other component is in the direction of the radial vector field. Okay, so let's say that this vector field has this orthogonal decomposition. Right, so in particular, this alpha is the scalar projection of this velocity onto the radial vector field. So this magnitude has to be greater than or equal to alpha. Alpha, the absolute value of alpha is just this length, right? So this length has to be greater than or equal to this. Alright, so how do we find this scalar projection of this velocity vector here? Well, by linear algebra, this is just gonna be the inner product of this velocity vector with ddr, right? But now, by the corollary of Gauss' lemma, this is just gonna be dr of this velocity vector. This integral is just greater than or equal to the following integral, right? The integral of dr applied to this velocity vector field. Now, what is this equal to? By definition of the one form dr, this is just gonna be equal to the value of this vector applied to this function r. But what is the definition of this velocity vector? It's just the push forward of ddt, right, under the map sigma. So really this is just ddt of r sigma. Thus, this is the integral of ddt of r sigma. And now we can evaluate this using the fundamental theorem of calculus. By the fundamental theorem of calculus, this is just the value of r at this point, sigma b naught. So value of r at this point, and minus the value of r at sigma a naught. So the value of r at p. Now rp is 0. Whereas, what is r of sigma b naught? This radial distance is going to be equal to this radial distance. It's going to be equal to r, this big R, because we assume that sigma b naught is this intersection of sigma, right, with this geodesic sphere. Of course, we need to be a bit more careful because there might be more than one intersection, so we need some technical assumption there. But those are just minor detail. Now, thus what we have shown is that this length, right, this length which is this given by this integral, this arc length is greater than or equal to r, greater than or equal to this arc length. And so this indeed is the minimal arc length from P to Q, so it's equal to the distance between P and Q. Thus, we have proven that radial geodesics are minimizing, and remember this implies that geodesics are locally length minimizing.